Hello and good afternoon, you all. Welcome to another of my videos about learning C with data structures. In the last few videos we've been looking at lists and hashes, and these are quite a commonly used data structure, but today we'll be looking at something totally different, and that is bitsets or sets or whatever people want to call these things. And they can be used as a more optimal data structure for doing specific things. Because you'd use the right data structure for the right task, right? That's how these things work. Now, I will be starting with some small examples to see how things are going, and then we'll build on top of that, and hopefully by the end of this hour, or maybe less, we'll see how that goes, we'll have an implementation of a bitset to do specific tasks. Now, the first thing that I want to look at today is how would you quickly determine whether a character is a vowel, for example. Now, in order to figure out where we have our vowels, let's have a look at the ASCII table, which I've found here on the man page, which has quite a lot of stuff in there. We can ignore that because nicely at the bottom, what I've done is they have a table of all the characters that are, for example, vowels. Of course, we know what the vowels are because these are the A, the E, the I, the O, the U, and the Y in some language or other languages. And in some other languages, the W is a vowel too. But let's stick to English vowels at the moment. Now, which are the vowels here? Well, we have the A and the A, the E and the E. And of course, the quickest way of determining that is, well, because there's only 10 in the ASCII set, is by just doing an if statement, right? You can do if A equals hex 41, capital X is 4 and 1. Or if you want to look at the decimal, the capital A is 60 plus 5, making 65, and you can do an if check. And that, because there's only 10 if statements, that is probably the best way of doing it. But it isn't very elegant. It'd be much better if you could reduce this set to just a simple check based on an index, right? Now, and the quickest way of doing that is, well, we can create a table, and this table we just mark out all the different vowels. So, for example, if we would draw that out, it looks something like this. So, see where it starts. My camera seems to be upside down. Let me quickly fix that. Okay, now of course it's not in the angle. There we go. Oh, I have done better than this. Let's see. Let's find out. There we go. That ought to do the trick. Sorry for that. I thought I tested that. So yeah, let's draw what we have here, right? So if we draw like the ASCII table, we do that by the letters. And I'm not going to draw all the tables. We have on the x-axis we have, say, the tens, so that is 0x and then the y and then the 0, and then on the other axis we have the x and then whatever we have in the z position. Then we can calculate them and come up with the ASCII numbers. We know that in ASCII we only take care of about the first part anyway, that is from 0 to what we have here is 127. And of course we need to divide that 60 times, or this one 8 times. My drawing isn't particularly very good. But you'll get the hint. And then this excess we have 16 as well. I know the boxes are getting smaller and smaller. I'm doing this by the second, so that it makes it a bit easier to halve every time. And this is column 0. We have 1, 2, 3, 4, 5, 6, 7, and then we have 1, 2, 3, 4, 5, 6, 7, 8, 9. Then of course we run out of numbers. And after, well, in hexadecimal you count with A, B, C, D, And then, oh, I missed the A goes there, sorry. My drawing is a bit off. We have E there and F there. Right, and then if we look at what we had in the ASCII table, we had, for example, we had the A was position 41. So let's fill in A 41. We know that this is a vowel, and the way how ASCII works, that means that the lowercase variant is 2 positions further, 20 hexadecimal further along. We have the E that's in position 45, so that is the 4, and then the 5, and then of course 65. We have the I, which is 49, and 69. We have the O, which is 4F. And then here, and which other ones do we have? We have the U, which is 55. 45, did I draw that correctly? 45. Yep, they're next to each other, just to make sure. And then we have the Y, which is 49, which is next to the I. It's kind of remarkable how these things work sometimes, isn't it? So this is basically the few elements where we have a vowel. Now, how would we go around writing a little program to test for these things without hard coding the if statement itself? So let's go back to some code and see if we can write this in code. So I have already prepared some other examples for later we're going to look at. The first thing that I'm going to have a quick look at is our makefile. And in our makefile, we basically have all, which means if you type make, it will do that by default. In this case, we're going to build something called test. The test is going to consist of two files, set.c and main.c. We'll touch quickly set.c because we are going to use that, but not quite yet. And then we compile this with GDB turned on. That makes our debugging easier later. So let's open up main and just let's hard code basically what we have here. Well, first we start with our main body of the script, which is always returning int. We have the name of the function, which is main, the amount of arguments that we have, and then we have the arguments if they're being passed in. In this case, we're not going to do it just now, but there we go. But yeah, that's something how we might pass in a vowel to see what it is. And then what we're going to implement, for example, we say printf is vowel, and then we either have yes or no if it is a vowel, and then what we're passing in here we'll look at in a moment. If it's a vowel, we do a ternary. If it is so, we say yes, otherwise no. There's not much to this at all, right? Let's go to our ASCII table. We don't need this anymore, but we can type make here and see what it says. We're getting some errors here. It's a warning that we have an implicit declaration of printf, meaning that we haven't pretty much defined what printf is. And it says here, include stdio.h to provide a declaration. So we'll just do that. Oh. Insert. It now warns that we have not defined its vowel and that we don't have argument, but that makes sense. We have not done this. The first thing that we have is our vowel. And our vowel is going to want an argument, which is a character, which is a letter. And then it either returns true or false, in this case 0 for false, and we'll fill that in a moment. But what is our argument here? Well, we basically want to set our letter, the letter that we're going to check for is what we're filling in. So if we would compile this now, it would work, it would compile at least, but if we run it, we get always no, because we don't do anything with the argument, right? So what we need to check is that we need to see whether we have enough arguments. If it is larger than 1, sorry, if it is smaller than 1, I should say, then we say no, we have nothing, printf usage, and this is again a common pattern to do. S, which we're going to put the argument in, and then we do letter. And as I mentioned in an earlier video, the program name is always in the first argument. So if we compile this now, you'll see that it compiles still. If we run it, we get is vowel now. That's odd. It should say our usage information. But remember, our first argument is our program name, so we need to check for smaller than 2. Our program name plus the argument. So we now run test row. It still says is vowel no, but that's only because we don't return. And it's also a common thing that you return something else, a negative number, if the program was doing something wrong. So we do make, and now we get another warning saying that we need to include stdlib, because that is what exit requires. So we'll include that too. Don't need to close this. We call make, and then we run tests. It says usage letter, and if we add a letter, it says is vowel no, even though it's a vowel because we have not implemented our is vowel yet. Now, the best way of doing this, or a simple way of doing this, is that we can do if letter is 0x, what did I say, 41, or letter equals, and so on and so on. But that is kind of annoying to do, so instead, or rather what you can do, which is even easier, is of course this. Or letter, and so on and so on, right? We can do that too, but that's kind of cheating. So instead what we want to do is we want to create like this matrix thing. And what we basically need is we need a, we create like this data structure, vowel matrix, where we know how long this is going to be. We're only going to look at the ASCII table, which is, well, the ASCII table is 128 bytes, but because the car type in C is a byte, makes it 256 elements, it's a safe way to do. And then pretty much, well, we need to define this, right? And yeah, how do you do that? Well, you can pretty much hardcode all the elements. So how many elements do we have? Well, we have 256, but we know that the first 3 rows are all zeros, are all null. So we need 16 zeros. At least we need that 4 times, because the first character, ASCII character, starts on position 41. And then we have at least this many at the end, because these are bytes 128 to 255. And then we have the place where we have our elements, our vowels is in this position, right, in this list. Yeah. Well, we'll fill this in a moment, what the positions are, but we can do if vowel matrix letter equals 1, we can do return 1. Oh, let me make sure that fits on the screen for you. And otherwise, we do return 0. Let's compile this. It compiles, of course. It'll still say vowel no for all of them because we have not specified which ones are vowels yet. But let's fill them in. So we remember this is line 4. And we know the A is here, capital A is here. Lowercase a is there. Then in position 5, 1, 2, 3, 4, 5, we have the the E and the U. Then on the 9th position, which is this one, we have the I and the Y. And then we had the O in the F position, I believe. And that's basically our bits filled in, right? Now let's see if this works. A still says vowel no. What about the uppercase? B? So what's going on here? What did I do wrong? I have no idea. let's see whether we have made a memory error. Let's run valgrind. Valgrind doesn't warn us about anything. There's one allocation, one free, which is, I don't know what it is. So what's going on here? Well, the best way to check these things is to use a debugger. We set a breakpoint in isVowel. We run. And we see that our letter is 0 here. Why does it say that? You see that here? Did we not fill in our letter? No, we didn't. Because the only thing we done was, of course, we defined our letter. We didn't actually set it. We still need to set our letter to our second argument. But we only want the first letter in it. If we didn't do this, you actually will get an error because the arguments are a string. And the string is a character pointer. So if we compile this, it actually warned us saying we did an assignment from a character to a character pointer. Makes integer from void without blah blah blah. What we need to do is the first character. Now, what we haven't checked yet is whether the first character is actually letter instead of the ending delimiter. But because strings in C are always guaranteed to have at least a null character in here, checking for the first character is always a safe operation. Checking for the second character, like this, is not always a safe operation because there could be just one character. There could be 0 characters, and that means that the second position is not defined. Anyway, let's compile this. We run make, no errors. We run our code. B is still no vowel, but now A is a vowel. And uppercase is 1. What about the I? Yes. The Z? No. And this is pretty much our first implementation. Now doing that with the vowels is of course a bit tricky, but you can also see already an issue, right? Or not rather an issue, but basically for every character we only need to know whether it is true or false. And what we basically have done here, we have created this data structure in memory that, well, we use 256 bytes for this pretty much, for only recording true or false for 250 characters. And a single byte can, of course, have 8 possible bits in it that we can use to determine whether there's a vowel or not. And that is pretty much what a bitset allows you to do. So let's convert our vowel matrix into a vowel bitset by using these as binary numbers. Now, in C, I'm not actually sure where you can use 0b here. I don't think that is allowed. So how do you convert this to a bitset? Yeah, that's a bit tricky, right? So maybe what we should do is write a little program that converts this to a bitset first. And how would you do that? Well, we need to loop over all the characters, and every 8 characters that we have, we need to do something about it. Now, this is going to be laborious, so I am going to ignore this. But first of all, how much is 256 divided by 8? Well, if we divide by 2, it makes 128. If we do that 8 more times, you end up being 32. And we can sort of see that because every line here is 2 bytes, 8 bits, and we have 16 lines for the 16 different hexadecimal rows. So the first few characters are simple enough, right? I mean, it's just 0, 0, 0, 0. And we do that 4 times because nothing is set here at all. And we do that 8 more times here. Now, of course, at this moment, what I will do is put this all on one line, because we don't really need that much space. But we need to do the same thing for these bytes here. Now, how do we go from pretty much 0, 1, 0, 0, 0, 1, 0, 0? Well, we can do the hexadecimal byte by byte. And that isn't actually very hard to do if you know how the positions work. Now, hexadecimal has 16 positions and bits have, of course, 2. So how do you convert from 0, 1, 0, 0 to a number? Is by remembering what the numbers are. So if you remember, this is the 1 position, this is the 2 position, and this is the 4 position. So pretty much, because it is only in a 4 position, it is basically a 4. Now the next one is also 0, 1, 0, 0, which also makes that a 4. So that's pretty simple. And we're going to reuse this number pretty soon. What is the number for 0, 1, 0, 0, 0, 0, 1? Well, that is simple enough as well. Is 0, 41, right? Now the next row is first a 0, and then a 4. And then we have a 4 and a 0. And we have this exactly twice because lowercase and uppercase letters are mixed, or sorry, are mirrored. Now, if we compile this, it should work. If we run this, it still works, even of course Z is much further in our code. And if you run valgrind to check some memory stuff, it still works, no problem whatsoever. Why did this? I don't technically know. But of course, every time we do a letter now, is always going to say no, because we haven't converted our letter to a position yet. And well, how would you do that? Well, let's have a look at that. Yeah, that is kind of a tricky way of doing this. Now, in order to explain this better, I will go away from this like hard-coded set of doing it, and instead we'll try to implement the bitset correctly from the start. Now, what is a bitset? Well, it's pretty much a number of states, a true or false state for each of the elements that we have. So let's define our first function, which is called a set, so not an xdebug set. It's called set, and then we do set create, and then we need to give it how many elements are in there. Now, the best way of defining an amount of something is using size t to define the size of something. And in this case, the size, we give it a size. So this is a set creation. We haven't defined our set structure yet, so let's do that too. What do we need to store in the set? Well, we have struct set. We need to remember how big it is. We do that by size. Size is not a great name, is it here, right? Oh, sorry, the size thing. And then we need to store our information itself, which we call set info, and we shall make this a void pointer because we don't really know what to put in here yet. So we call it set info, which is going to contain the information in our set. Now, what operations are we going to do in the set? Well, we're going to be able to, well, we need to create it. So let's call it set ctor, which returns our set. And of course, we have our size t. I'm using ctor because that is the standard sort of way of doing it. We will have a set dtor. So extract pointer, which is our set. Sorry, I should return a pointer to a set. And then of course, we need to set an element in there. And we call that void set. We need to give that a position. We need to set unset a position, and of course these functions also need to get our set attached to it, because this is not object-oriented programming. So we need to pass it in, and then we have a function Isset. That's pretty much our methods that we need to implement. So let me copy these to our C file. Make sure to include our set.h file. And of course, as usual, we really need to define our guard here. So if null def set h, this is all to prevent, of course, the same header file from being included multiple times, and hence declaring the same function multiple times. And if, and then in this custom to show you which one the end of is, to keep track of that. And now, yeah, we need to implement these methods. Now, what is the size of a set? Let's do some standard definitions first. This is just our structure that we're going to create in here, and then return, because this is our constructor where we return our objects. Well, we need to first of all create our set itself, which we do by doing memory allocations. We say calloc, which is allocating the memory and setting it all to 0. In this case, that doesn't make a lot of sense because we're going to set all the elements ourselves anyway. And then what we need to do the size of is we need to create as many bytes as make up our set structure. Which is in this case, this size t element, which is going to be 4 or 8 bytes, and our pointer, which is going to be 8 bytes because on the 64-bit platform. We'll pretty much just need to fill in our variables. But what do we do for set info? Well, we need to allocate memory, and we need to allocate enough memory for creating our bit sets. And in that case, if our size is 256, we basically need to define the size by 8 to get from pretty much bytes to bit, right? So we do size divide by 8. But this gives some problems because if our set size is 7 and we divide by 8, the answer is 0. And we don't want to do 0, of course, because that means we don't allocate any memory at all. And we do need to allocate at least 1 byte. But we are doing this with integers, so we can't simply use round or void on things like that. So how do you make sure that we always have at least 1 byte? Well, we need to make sure that we add 1 to it unless the number was exactly divisible by 8. And the way how you do that is by using a modulo. In this case, we do a mod, and that returns the number that didn't fit in the division. So if you divide 7 by 8, a normal division returns 0, but size, or 7 modulo 8, will return 7. Of course, we don't want to add 7 bytes. We only want to add that if it is not null. So this is pretty much, sorry, I'm doing this wrong. This is pretty much how much memory you need to allocate, and I've forgotten to add malloc in front of us. In Vim, there's this handy trick where if you press the %, it switches back to your other parentheses, which makes it kind of handy to make sure you have enough of them. And this is pretty much allocating our set to making sure that we allocate the right amount of information. What we do in the set detour, that's pretty simple too. Pretty much what we need to do is, well, we need to free our set info. And the other thing that we allocated was our set itself. So there we go. So that's pretty simple. Now I am going to get rid of the matrices here, and this vowel we will re-implement at some point soon. Now the question is, of course, how do we make sure that we indexed the right bit instead of the right byte? And we'll create a temporary function for this, where we would calculate, well, it returns 2 things really, doesn't it? So in C you can't really return 2 elements, because what it needs to return is it needs to return the position as well as the bit in there. But you can only return 1 variable, so the way for doing that is to use something called out parameters. So our position is our entry, and then, yeah, to put something out, you need to use a pointer reference to get it out. So in this case, we have our byte that is going to get out, which you need to specify as a pointer to it, because we pass in the address, and then the function can update the information that is stored at that address. And we need to do the same thing for the position in a bit. Yeah, there is not a argument that is only 8, but bit will do. And now what we need to do is we need to return this position to the byte. Now, calculating what the byte position is simple. It's pretty much the position divided by 8. Right, that makes sense. And then the bit position is also easy to calculate, because it is pretty much the position modulo 8. And that then calculates the bytes and the bits. And in order to make that a bit clear, let me go draw what I'm actually trying to do here. If we go back to our diagram, if we have, say, a set of 16 elements, right? We have 16 positions in 2 bytes. So we have our 2 bytes here, and each of them is 8 bits long. And I'll make the one in the middle a bit thicker so you can see what's going on there. And then we need to map our 16 values from 0 to 15 onto that set. If we calculate, this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and 15. So the first thing that we need to calculate is this byte. So we know that anything from 0 to 7, the byte is going to be 0. And from 8 to 15 is going to be 1. And we can calculate doing that 0 dividing by 8. Well, that's of course 0, blah, blah, blah. 7 divided by 8 is still 0. Oh, sorry, 0. And then 8 by 8 is 1. So that maps to the right byte here. But in order to get to the right bit, we basically need to take the modulo of it. So if we take 7, the modulo of 7, modulo 8, is 7. And 8 modulo 8 is 0 again. So that quite nicely counts the bits from 0 to 7. And then in the second byte, it counts from 0 to 7 again. So with the first one, with the division, we calculate whether it is the right byte, and with the modulo, we calculate the right bit. So for example, 7 then forms this one. So this is how we calculate from between the bits and between the positions to our position in the set. But of course, when we just have the number 7 itself, we can't really do anything with. We need to match that to the right bit. And yeah, here if we would look at memory and pretty much want 0 at the 0 position, we need to calculate some additional magic. But if we flip this around, which we can easily do, so we go from 7, I'll draw the line here to make it a bit more obvious, and do that twice. Then we can very much easily calculate from a bit number to a number that would fit this whole thing. As you remember, we had the 4x44 that represent, oh, that falls off my screen here. The 4x44, which matched our number here, right? We calculated that by the first one being 1, 0, 0, and that matches to this row. So we get 0, 1, 0, 0, 0, 1, 0, 0, and so on and so on. So this 4 number matches basically to this bit here. And then the second one matches to the other one here. But how do we go from 7 to the number that we actually need, which is 128? Because this is the 128 position if you consider this a byte, and this 64 and 32. 16, 8, 4, 2, and 1. So we need to go from 7 to 128. Now it is kind of easy to do if we start at the other side. So if we have the zeroed bit, well, how do we go from 0 to 0? Well, that's simple. It's the same, right? But if we have this position here, that is bit 1, but how do we go to the number 2? Well, you basically shift it left by 1. That basically, this operation here, the shift operation, basically alter 0 to the end and then shift the bit to the one before. So that then easily calculates to 2. And you will find out that if we do that for the second bit, or say the third bit, if we do 1 shift right 3 times, so we start in with the 0 position, which is 1, shift once, we get to the 2 position, shift once, to the 4 position, and shift once to the 4th position. And if you look at this, then if you do shift 7, 7, which is our highest bit number, you end up getting in this position here. So doing the shift position worked quite easily. Now, so what we can decide is, instead of returning just the modulo here in our code, what we've done here is, what we can actually do is already convert that to our right bit by setting it right on. By pretty much taking this position and doing a shift of that the right amount of times. So now this is of course not the bit number anymore, but the bit value. And that should be good enough to do our set. So let's implement our set method. Well, first of all, we need to calculate our position. So we have unsigned cars, we have the byte and our bit value. And we calculate that with our function that we've just implemented, which is position to byte and bit. We feed in the position, but because we need to update the values in this function, we need to pass in the address of those values so that the function that we call can update that through our pointer. And the operator for taking an address of something is using the ampersand. And we do that twice. And now we know that the byte that we have, which is the first entry in the set, we basically need to OR with the value that comes out in the bit value. So we can do a set info, which is our data structure. We have our byte, which is our byte index. And then we can simply set that to what we already have in there. And then we OR that with our bit value. And the OR operation basically takes any bit that we've already set here with the bit that we are going to set. So for example, if we started out by an empty set, say we have our 2 bytes here, and it starts with all zeros. So I'll do this in, well, we get 4 zeros, 4 zeros. So I meant 8 to say 8. This doesn't fit. And only a 7, but forget about it. We'll draw 8. If we then add our bit value to it, in this case our number, if you remember, we get 0, 4, 0 for our 1 bit, which is our 6th bit. So this would have been our 7 bit, so let's use that. And basically, if in binary, that looks like this. And what the OR operation does is basically takes any bits that we have above the line, and if one of them is a 1, it will then return 1. So in this case, we'll get out as a result pretty much that we put in. But if we then set, for example, the second bit, which is our 2 value, which is 0, 0, 0, 0, 0, 0. If we then set that bit, we do this calculation, we end up with this number, which hexadecimal is of course 82. And that is pretty much the way of flipping bits to do what we need to do. And that is basically what our set function now does. Now doing the opposite, unsetting, is pretty much done in the same way, but with a different operation. So we can pretty much copy this, but instead of doing an OR, what we want to do is we want to negate what we have just done some. And a negation is the same operation as doing an AND, making sure that everything matches, but with the opposite value. And I will draw that out in a moment as well. So the operation for that is, or the symbols for that in C are the following. And that is the opposite information, the opposite way of doing it. And again, I shall draw this again out as well. So let's see that we start with our value that we have here. And I'll just focus on the first byte here, which is our 0x82. And say that we want to unset our second bit, which we know is hex 0x002. So let me draw that out as well. But yeah, we can't use an AND. If we use an AND, then we'd only get this bit out, right? The AND operator making sure that if both of these bits are set, then the result is 1. But we want the opposite. We want to make sure that we only keep all the bits in here if this bit is not set. So that means we need to flip this around, which is our tilde operation. And that makes that into... That takes up a lot less. Oh, sorry, that's 4 ones. That is our tilde operation, and that then, well, how much is that in hexadecimal? That is F D, I believe. Doesn't matter. I'm just trying to do this in my head. And then, of course, we can use an AND of this one, and everything where both of them are set, we're going to keep. So this one doesn't get set because it's only in a negative one. This one gets not set because it's only set here and no longer here, and so on and so on. And the only one that's being set now is our first bit, meaning that we have the 80 out, and that is exactly the opposite of doing this operation where we set this bit. We now unset this bit by removing this 2 from it, and we end up at our set with it unset. And again, that is of course the operation that we have just implemented. Now the only thing to still implement is to make sure that our bit is actually set. Now we can copy and paste our calculations again, but of course we don't want to set the value, we just want to check what actually the value in here is. And that is pretty much as simple as we return our the value 1 if the bit that we want is set. And you can easily do that by checking whether our bit value is set. Again, if you look at the drawing, forget that we did a negation here. If we want to check whether our second bit is set, we compare our bit field value that we have here with the mask that we had here that we already calculated, and basically we need to make sure that, well, if what we match, if what we want to test for is this bit is set, and you do that with the AND operation, then the result of that is 4 zeros, because those are, although this bit is set, they are not part of this. And then only in this case is the bit set. And then, because this is not 0, we can just return this value to get our number out. And that is pretty much our simple set implementation. Now let's actually make use of our set implementation. So we are going to include our H file. We create a function that sets all the positions for all of our vowels. what do we call this? Configure set. We pass in our set that we have to create first, of course, and that it basically updates the set file of operations. So we do set. In our set, we set the A. Now, the nice thing that in C is that if you use a character, it also is a number. It's basically its ASCII value. So we can just copy and paste this. Let me do E, O, U. No, that's not how the alphabet works. And the Y. Let me switch back to actually our screen of code so that you can actually see what I'm typing here. And copy that over so that we can do it for the lowercase variants too. Of course, usually you get this information from somewhere else. By the way, the trick that I did is I Ctrl V to select all of them, and then I do the tilde. That converts in Vim from uppercase to lowercase. It's kind of handy. You don't have to copy and paste this or retype the letters. So that basically sets our set. And then is vowel, well, we pass in our set information. And our letter. And then we do if set is set. We use our set and our letter. We return 1. And otherwise return 0. Then the only thing that we need to do here is we need to create our set. Vowels. And then we have our letter still. Well, we don't do anything if we don't have to do anything. We do vowels is set ctor. We know how big it's going to be. It's going to be 256. We do, what do we call this? Configure sets, which is configure sets. We pass in our vowels just to set things up, and then we can check with is vowel again whether it is set or not, which we do there. And of course, we do need to free our set at the end. Now, of course, the big question comes is, has all the typing actually worked? You should see the rest of my code here, actually. So get my face out of the way and you'll see what I've done in the bottom by freeing up my set as well. Let's have a look at our code and see whether it compiles. Make. Oh, we have some errors here. That is good. We're going to have a look at this. Well, the first error that says in line 46 we do is vowel letter, but it wants a character. So we messed that up. Because our position, line 46, is what it said, right? Line 46. It says that although our letter is a character, what did it want as type? It wants... what we haven't passed in is our vowel set. That's our problem, and of course, that is also the name of our set here. So let's fix that too. We'll make... We still have one more error on set.h line 10. Oh, simply forgot my semicolon there. And now we have some definition issues because it doesn't know what size t is. So let's add that as well. Can never remember which one is in which. Luckily the compiler helps. Now we have a few more errors. We need to define the one from malloc as well. In our set, all the things, what do we miss? We have some other issues. So let me clear this. So what does it say here? It gives quite a lot of warnings that all look the same. It says in lots of places dereferencing void pointer. If you remember that in the set we actually defined this as a void pointer. Void pointers are special in a way that the C compiler doesn't know what to do with it. It is a pointer to a data type that it doesn't know anything about. So what we really need to do is use a character pointer, because we basically have a character array which is also unsigned to define our sets. And let me just iron that out. So let's compile this again, and now we get no errors whatsoever. Let's hope that the program runs. Let's run it for test B. It says no. Uppercase A. Yes, it says yes. What about the P? No. O. Yes. So this seems to work. Let me just run this with Valground to make sure we don't messing it up. We're getting 3 Alex and 3 freeze. So there we have it, our first set implementation. Now, doing this for vowels is a bit pointless. And there are many other situations where using a set actually does make a lot of sense. But we have run out of time to go through some of the more useful examples, because in this case where we have the vowels, basically we only have 12 out of 256 characters that are a vowel. And implementing, of course, a whole data structure for this in this way is not very efficient. I mean, by far the fastest way, instead of vowel, the fastest implementation would be something like doing something like this. You do case A, a case A, and so on. And if all of these match, return 1, and otherwise return 0, right? I mean, that is going to be way faster because we have such a small set of elements that fit. But of course, this is hard coding whether we have vowels, and if we need to look at data that comes from a different source, then we can't hard code it anymore, and this is where then sets become more useful. But as I said, we'll go have a look at some more useful examples in the next video. Thank you very much for watching today, and I'll be back next week with some more sets.